Hi everyone. For those of you that showed up today, happy Friday. And we won't have learning catalytics today, so I guess some of you were overjoyed with that. We're also not going to do a lot of coding this time. We're going to do a lot of math, so I hope you had your coffee this morning or tea or whatever it is you need. First I want to go over just the topics we're going to go over today. First, we're going to find the connection between the Poisson random variable and the exponential random variable. Then we're going to compute mean and variance for the Poisson random variable. Then we're going to look at expected value of a function of multiple random variables. Then I'm going to go through more properties of expectation and variance operators. Then, second to last, we're going to look at joint moments and joint central moments. And we'll end with the special case of covariance, which is the 1/1 central moment you'll see of two random variables. So let's get started with today's lecture. We'll look at Poisson points. So a Poisson point process is a process in which events occur randomly in time at a rate lambda, a number of events per unit time. So the setup is from 0 to t to 2t and so on. We have some random number of events. We don't know how many, so we're going to characterize this random variable n, which is the number of events that occur in this t. We're looking at an interval of length t, and we can repeat that an infinite number of times as well. But n is a random number of events in that unit interval of length t. And we'll characterize it as a Poisson random variable with parameter alpha equals lambda t. So we want to find what's the mean of n. So this is equal to the sum from k equals 0 to infinity of k times e to the minus alpha times alpha to the k over k factorial. So this isn't so easy to compute in this form, but we can look at the PMF real quick. And this is equal to the probability that n equals little k. So let's look at just the PMF. Which equals 1. And I think something nice will pop out if we just take the derivative of this with respect to alpha. And we can move this to the other side. So if we take the derivative of this with respect to alpha, we get k times alpha to the k minus 1 over k factorial equals e to the alpha, right? Because derivative of e to the x with respect to x is just e to the x. So looking at this, we can see we almost have it in this form, but we need to multiply through by alpha. So if we multiply through by alpha, let's go to the next page. We get k to the alpha to the k over k factorial equals alpha times e to the alpha. So if we move this back to the other side, we get that implies that the expected value of n is equal to alpha. Does everybody see how we did that? So we took the derivative of the PMF and we almost had it in the form of the expectation. So that worked out nicely. Let's also find the variance of n. Let's go back a couple pages. Let's find the variance of n. That's equal to the expected value of n squared minus the expected value of n, quantity n squared. So we just found what the expected value of n is, so we can square that and get that, but we don't have the expected value of n squared. So let's write out the PMF again. move this to the other side again. And because taking the derivative with respect to alpha the first time to get the first moment worked well, I think taking the derivative 2 times will yield something meaningful. So let's take the derivative with respect to alpha twice. So if we do that, bring the derivative inside of the sum, the 2 derivatives, we get k times k minus 1 times alpha to the k minus 2 over k factorial equals e to the alpha. Again, take a derivative an infinite number of times, it'll still be e to the alpha. Only something interesting is happening on the left side of the equation. So we can see if we multiply through by alpha again twice and get an alpha squared over here, we get something interesting. So multiply through by alpha twice, we get the sum from k. Alpha twice, we get the sum from k equals 0 to infinity of k minus 1, alpha to the k over k factorial equals alpha squared, e to the alpha. Bring that back to the other side. And then we recognize that this is the expected value. Let me erase this. We recognize that this right here is the expected value of n times n minus 1, which is equal to alpha squared. But this is equal to the expected value of n squared minus the expected value of n. All of this is equal to alpha squared. So now we know that this implies that the expected value of n squared is equal to, add to both sides, we get alpha squared plus alpha. So now we can compute the variance because we have the expected value of n squared and we already computed the mean. So then the variance, thus the variance of n is equal to alpha squared plus alpha minus alpha squared equals alpha. That's pretty interesting, isn't it? Because that's saying that the expected value of n and its variance are equal to each other. That's characteristic of the Poisson random variable. Now let's consider the Poisson arrival process. So we just look at the Poisson point process. So if we go from 0 to t, and you keep stacking those intervals of length t we care about, that's our unit of time. It could be an hour, a day, whatever. And we have random events that occur. We want to look at the inter-arrival time between events. So we'll denote that with random inter-arrival time with the capital letter T. That's what I just said. It's the time between 2 events. Then we want to find what is the expected value of that inter-arrival time. And how does it relate to the expected value of n, the expected number of events? How does the expected inter-arrival time relate to the expected number of events? So let's work that out. Let's ask, what is the probability that t is greater than the length of our interval of interest? So let's work that out. So let's just look at this real quick. We're asking what's the probability that t is greater than little t. That's equivalent to the probability that we have no arrivals in 0 to t, which is equal to the probability that n equals 0, which equals e to the minus alpha times, raised to the 0, so this ends up being times 1 because you divide by 0 factorial. So you get e to the minus alpha which is equal to e to the minus lambda t. And this isn't quite useful yet, so let's ask what is the CDF for t. That's equal to the probability that t is less than or equal to little t, which is equal to 1 minus the probability that t is greater than little t, and that's equal to the 1 minus e to the minus lambda t. So all this math is showing that t is distributed exponential with parameter lambda. So the interarrival time is exponential, but the number of events occurring is Poisson. So this implies that the expected value of t is equal to 1 over lambda, because we know that from exponential random variables. So that's the connection between Poisson random variables and exponential random variables for point processes or arrival processes. So now let's move on to the next topic for today. We're going to look at the expected value of a function of multiple random variables. So if you remember the Lotus rule from last lecture, whatever this function g is of multiple random variables, you just stick it into the double integral, or however many integrals there are, and multiply by the joint density. And that'll give you what that expected value is. So let's do a specific example, a sum of two random variables. So you have z is equal to x plus y, where x and y are not necessarily statistically independent. So you plug in z, so now we get the expected value of x plus y, and we can use, we'll make use of the linearity of the expectation operator. But first, let's just distribute the joint density into x, and then distribute the joint density into y. And note that right here with this inner integral, that we're marginalizing out y. And here, for the outer integral, we're marginalizing out x from this integral. So we're dropping an integral when we're doing the marginalization. Can anybody tell me what these two integrals are?
Expectation of x and y.
Yes, but exactly. Great. So in general, the expected value of the sum of n random variables is equal to the sum of the n expectations. And that this holds whether or not xi are statistically independent. It doesn't matter if the xi are statistically independent or not. Like, because of the linearity of the expectation, that'll always hold. And a bit more generally, if we look at the g sub I of vector x is equaling to g sub I of little xi for all I, then we can apply linearity again where the ai are little weights or constants, and we can swap the expectation with the sum to get a simpler expression to work with. As another example, say we have x, y, which are statistically independent, and we look at g of xy is equaling to the product of a function of just x and a function of just y. If we take the expected value of g of x and y, we can note something interesting. And then switch colors. We're regrouping the terms based on x and regrouping the terms based on y. So in the case of independence of x and y, you can rewrite it as the expected value of g1 of x times the expected value of g2 of y. In general, if the xi are mutually statistically independent, we can take the expectation of a product and turn it into the product of the expectations. Note, however, that 17 being true does not imply that the xi are mutually statistically independent. It's a necessary condition, but it's not a sufficient condition. So that means the forward implication holds. So if the xi are statistically independent, then this will be true. But if this is true, that doesn't imply that the xi are statistically independent. Just want you to know that. And we'll see the forward implication at the end of lecture when we cover covariance. You'll see the forward implication of this. So let's do an example. Let's look at the variance of the sum of n random variables. So if I want to compute the variance of the sum of n random variables, this is equal to the expected value of the sum of n random variables minus the expected value of the sum of n random variables squared, everything squared. And we can apply one more simplification to this. We can swap the expectation and the sum. And that's about all we can do for this like general summation of n random variables. But let's take capital N to be 2. So let's look at 2 random variables. So let's look at the variance of just x plus y. And if we go back and look at this, we can see what we get. We get the expected value of x plus y, and then you subtract off the means. Squared. And from this, we can regroup terms. Y minus mu y, all things squared. Then if we FOIL, we get expected value of x minus mu x squared plus the expected value of y minus mu y squared plus 2 times the expected value of x minus mu x, x times y minus mu y. And can anybody tell me what these first 2 terms are?
The variance of x and the y.
And a variance of y, yes. So this is variance of x plus the variance of y plus 2 times the expected value of x minus mu x times y minus mu y. So we know what these first 2 terms are, but we don't know what this is yet. So let's work on that a little bit. Minus expected value of x times mu y minus mu x. Right, you can pull constants out of expectations. Minus mu x times the expected value of y plus mu x mu y. And this is just the mu x, and this is just the mu y. So you can canceling the last 2 terms simplifies to 2 times the expected value of x times y minus, you just have one of these terms left over, mu x times mu y, and that's that. But I want to make a note on this. Note that in general, the variance of x plus y does not equal to the variance of x plus the variance of y. Only if they're statistically independent does this split in, using that property we derived, into the expected value of x times the expected value of y, and this cross term would go to 0. But otherwise, you can't say in general that, because the variance is a nonlinear operator because of the squaring, so it destroys the linearity. But also, so if you have, say for, if you have a, in general, but for a set xi, if all xi are statistically independent, then you can write that the sum over all I, or excuse me, the variance of the sum over all I of xi is equal to the sum over all I of the variance of each xi. You can say that if all the xi are statistically independent. So let's move on to the second to last topic, joint moments and joint central moments. We define the jkth joint moment of x and y as the expected value of x to the j times y to the k. And applying the Lotus rule, we just plop that in there with the double integrals and the joint density. And the jkth central moment is similar to the joint moment, except you subtract off the means from each of these factors before you plop it into the integral expression. And so that's the joint moment and the joint central moment. And looking at this, if j equals k equals 1, we arrive at what the covariance is of x and y. The covariance of x and y is the 1/1 central moment. And if we FOIL like we've done previously, we get this pretty expression, we get this cross term appearing again. And note that if either mu x equals 0 or mu y equals 0, or both are equal to 0, you get that the covariance of x and y is just the expected value of x times y. And like I said previously, if x and y are statistically independent, then you get that the covariance of x and y is equal to 0. And we're doing great on time. So we're going to end a little early today. But for those of you that came, just sign your name on this sheet of paper up here if you want some points. Yeah.
Could you just go back to the last couple slides and try to get the points down? One more. There you go.
Here?
Yeah.
Is this good? Yeah. And yeah, I guess I can take questions too. If anybody has any questions, I should give an opportunity to ask questions. Was it pretty clear? Oh, yeah.
The next slide, if their SI was 0, right?
Previously?
Forward.
The forward side.
Yeah, the forward side.
Here?
Yeah, that was just
This?
0.
Yeah.
Yeah, okay.
Exactly. Any other questions?
So this,
Yep.
this top bullet point, so that's if either mu x or mu y or both are 0.
Yeah, then the covariance is just the expected value of the product of the random variables. And that comes from right here. Haven't figured out whether I'm going to penalize students who didn't show up today or reward those who did come. So we'll see.
I think reward is always better.
Yeah, reward.
That's